very bodies. They sustain modern life and are essential to every advanced tool built by human beings. They can take us to the heavens or destroy us. Now, heavy metals on Modern Marvels. They come from the dawn of the cosmos and the fiery hearts of dying stars.
Heavy metals are cooked in the center of a star. As a star is born and lives its life, it comes to a phase at the end where a bunch of processes happen very rapidly and the star explodes, and in exploding scatters out a group of heavy metals that reach all the corners of the universe.
Metals now found on Earth came from one of two sources. Space debris that collected as the planet formed 4.6 billion years ago. Or meteorites that have since struck. They endure through an eternal life cycle of endless transformation.
They're found, manipulated, relied upon in ways that we totally take for granted, and then they're discarded and reused again. They're completely recyclable in most cases.
Metals make up 2/3 of the known elements. An element is defined by the number of protons, neutrons, and electrons that form its atoms. The periodic table lists elements in ascending scale based on atomic number, the number of protons in each nucleus.
Periodic table is a way to organize the elements that occur naturally in the universe and ones that can be created by unnatural processes into a sequence that starts with the lightest element, hydrogen, and progresses up to the heaviest natural element, uranium. And on the progression, somewhere around 26, iron, is a breakpoint where anything heavier could be regarded as a heavy metal.
From the earliest days, human progress has been tied to the mastery of metals.
The advanced civilizations all use metals for cooking their food, for transportation, for work, for agriculture, for defense.
The average American baby born in 2006 will require 45,000 pounds of metals during its lifetime to sustain its standard of living. Heavy metals such as iron, lead, zinc, nickel, and copper are so essential to America's economic and military might that they are stored in the National Defense Stockpile, a $10 billion collection of materials ready in case of all-out war. In a national emergency, no metal would likely prove more decisive than uranium. With an atomic number of 92, uranium is the heaviest of all elements, 18.7 times denser than water. Its naturally occurring radiation generates tremendous power from within the Earth's core, more than twice the level of global human energy consumption.
You can account for about 30 trillion watts in the form of radiation coming from the uranium-238 that was captured when the early Earth was formed in the core. That now acts like a small nuclear reactor. It's a natural source of heat that has to make its way to the outside of the planet, and it brings up quite a bit. And volcanoes today are living proof that something in the core of the Earth is generating a lot of heat.
The introduction of the atomic bomb in 1945 heralded uranium's immense potential as a destructive force. But splitting the atom also unleashed a vast, peaceful source of energy. There are 103 nuclear reactors operating across the United States, generating nearly 20% of the nation's electricity. Worldwide, 430 reactors help power 31 different countries. Like other metals, uranium is extracted through either underground or open-pit mining. The ore is pulverized, then treated with acid to dissolve out the uranium.
Uranium is radioactive, but it's not super radioactive. You can hold ore in your hands. You can actually come up to a fresh fuel assembly and inspect it very closely.
Uranium must be heavily processed to produce usable fuel. It's converted into a gas so that uranium-235, the fissile isotope needed to create a chain reaction, can be enriched from its natural state of 1% to 3 to 5%. After enrichment, the gas is reformed into uranium dioxide and molded into fuel pellets. The pellets are placed inside metal tubes and assembled into bundles for the reactor core. The civilian nuclear power industry grew out of the Cold War and the global arms race. Ironically, fully half of the uranium that powers American reactors now comes from dismantled Soviet nuclear weapons.
We get an economical source of the uranium, and better yet, about 10,000 Russian warheads have been destroyed in this process. And under the deal with Russia right now, it'll be 20,000 weapons destroyed and used in U.S. Reactors to produce electricity here.
Nuclear fission converts matter into energy that's released as immense amounts of heat. In nuclear reactors, uranium acts as a trigger, the initial power source for what eventually becomes electricity.
In a nuclear power plant, the uranium forms the heat source, and that heat is then transferred over to water, which heats the water, and the hot water does the actual work of driving a turbine, very much as it would in a coal-fired or an oil-fired plant.
But nuclear fission is supremely potent. A uranium pellet the size of a peanut generates the same amount of energy as 1,780 pounds of coal, or 149 gallons of oil.
Underneath that pool of water and that stainless steel head is a dry well compartment. That compartment contains the reactor vessel. That reactor is currently operating at 100% power, supplying the energy needs of over 1 million people.
The most visible part of a nuclear power plant, the cooling tower, is actually the safest. Towers like this one at Grand Gulf Station in Fort Gibson, Mississippi, merely release steam, which is a byproduct of the generation process. The vapor is inert, and a cooling tower could be destroyed without releasing any radiation into the atmosphere. The reactor is the heart of a nuclear plant. Elaborate security systems, multiple engineering redundancies, and backup power sources all have a single ultimate goal: to ensure that the nuclear rods stay underwater and under control.
The concern is making sure we always have enough water to keep a sufficient level above top of active fuel to keep from having the fuel bundles get too hot.
The bundles generate such intense heat that if not adequately cooled by water, they would quickly begin to melt their containment vessel and release radioactivity. This happened at Chernobyl in 1986. Nuclear rods decay over time, and after 5 years are transferred from the reactor to a nearby spent fuel pool. Uranium isotopes continue to radiate considerable heat, so rods cool in the pool for 10 to 20 years before they're ready for dry storage. Because they remain radioactive for thousands of years, safe long-term storage presents a difficult and as yet unresolved dilemma. We now return to heavy metals on Modern Marvels. While nuclear power and atomic weaponry employ the same raw material, uranium-235, a warhead requires uranium at a bomb-grade purity of nearly 90%. This mountain range north of Moab, Utah, played a unique role in the history of uranium mining. When the Soviet Union shocked the West by detonating its first atomic bomb in 1949, Cold War fears raged. In Washington, the Atomic Energy Commission decided to enlist civilian help to build the nation's uranium reserve. The AEC raised the base price for uranium ore and offered a $10,000 bonus for the highest grade material. Eastern Utah was well known for its uranium deposits, and thousands flocked to the region. Anyone with guts, vision, and luck had a chance to make their fortune. But few possessed those qualities in greater abundance than an unemployed Texas geologist named Charlie Steen.
Charlie hitchhiked down Highway 191 and walk in here for 3 days at a time. He'd pack all of his food and water. And then he wandered all through the hills and the canyons around here looking for his idea of what would be favorable areas for the discovery of uranium.
In 1952, Charlie drilled a discovery hole in the Movita Plateau.
And he had to borrow a friend's Geiger counter to actually discover that, yes, it was uranium ore.
Charlie Steen had discovered the single largest deposit of uranium in the United States. Soon, this tunnel was built to exploit his claim. Word of the find triggered a human stampede.
There were all kinds of magazine articles about come down and get rich, you know, buy this Geiger counter, it's guaranteed to find you something. It's just like the gold rush. There was a lot of hype and misinformation.
There's legends, you know, stories of people renting small planes and throwing claim stakes out of the planes to try to cover as much ground as they could and tie up as much as they could.
Virtually overnight, Moab went from a sleepy hamlet of 1,200 to a boomtown of 5,000. All dreamed of striking it rich. Few actually did.
I was like some others, just going along and checking every rock that might look like I have ore in it. Sometimes you'd get excited and sometimes you wouldn't, because there's a lot of different rocks that do have radiation.
The AEC eventually phased out subsidies to private miners. The uranium market stabilized, and like all rushes, the great Utah boom turned to bust. But Moab would never be the same.
Moab was the first place in Utah that had liquor by the drink. It changed the culture, it changed the economy, it made a much more diverse culture here. It had a huge impact on Moab.
Today, rising oil prices have renewed interest in peaceful nuclear power. The United States is on the verge of granting permits for the first new construction of nuclear power plants in 30 years. And miners are once again scouting the hills near Moab, betting that uranium will one day make them rich. Uranium plays a key role in 21st century life. The vast construction projects that helped define the 20th century were made possible by the heavy metal iron and its steel alloys. The accident at the Chernobyl reactor released about 400 times as much radiation as the atomic bomb dropped on Hiroshima. Heavy metals will return on Modern Marvels. We now return to heavy metals on Modern Marvels. We live in a world of steel, which has the combination of strength and flexibility that makes ideal frames for large modern structures. Steel, which is stronger and more pliant than iron, is simply iron plus less than 1% carbon. Iron has an atomic number of 26. Today, metal production is dominated by recently devised steel alloys. Steels mixed with a variety of heavy metals. These fiery furnaces at Middle Steel USA, outside Chicago, appear much as steel factories did a century ago. And the basic stages of production, smelting, melting, and casting, are also much the same. But here, up to a dozen other metals are added to the molten steel in precise quantities in a closely guarded recipe. Even minute amounts of selected minerals, sometimes as low as 1 part in 5,000, can change the properties of the final product. High-strength alloy steels form the safety carriages of cars. Special armor alloys gird naval vessels, protecting against corrosion from seawater and the impact of torpedoes. These so-called superalloys have made steel more valuable than ever. But before our modern age of steel, other heavy metals had their day. Today's periodic table lists 86 metals, but until the 12th century AD, humans had discovered just 7, all heavy, known as the metals of antiquity. Gold and silver were soft and used mostly for ornamentation. Mercury, also known as quicksilver, is the only metal that is liquid at room temperature. It was widely used to dissolve gold and silver. Tin, lead, and iron served important functions, but only after the age of the 7th metal of antiquity, copper. Approximately 10,000 years ago, copper became the first metal manipulated by man. But copper tools were rare until the discovery of smelting, the process of heating copper oxide to produce greater and purer quantities of copper. Copper tools and weapons were soon improved by the addition of other metals.
The next stage in development was to combine metals. So for example, combining copper and tin gave you bronze. It's harder than either copper or tin, so it made superior weapons.
Better weapons meant the capacity to conquer and rule. By 2000 BC, metals were essential commodities, powerful forces shaping the destinies of empires.
The early cities were basically built around trade in many of these objects, and one finds tin coming from Anatolian Turkey, one finds copper coming from Africa. Trade in metals was an enormous part of the economy.
Metals possessed such miraculous properties that many ancients believed they were alive. In the 3rd century BC, the philosopher Aristotle theorized that metals grew underground, much like seeds. The ancients appreciated iron's special properties of strength and malleability. But before iron could be shaped, it had to be heated to near its melting temperature of 2,700 degrees Fahrenheit. Such heat was difficult to produce until roughly 1000 BC, when a new technique raised furnace temperatures dramatically.
The lever's attached to a bellows. A bellows is an air pump. By blowing air into the fire, we can just about double the temperature. When I put the bar in the fire, it's at a black heat, below 1000 degrees. As it heats up, it'll turn red at about 1000 degrees, then go from red to orange, to yellow, to white hot. White hot is close to the melting temperature, about 2,700 degrees Fahrenheit.
Iron is abundant and thus inexpensive. It's strong, durable, and can be forged and welded into pieces of virtually any shape and size. Since well before Christ, iron reigned as the best substance for making everything from household goods to weapons of war. In the 18th century, iron masters changed their fuel from charcoal to coke, a charcoal derivative that burns harder and hotter, and constructed much larger furnaces. In the 19th century, steel replaced iron as our primary construction material. Blacksmiths had long struggled to remove the existing carbon from iron and then add back precisely the right amount to create steel. In 1856, English engineer Henry Bessemer discovered that blowing air through liquid cast iron created a reaction that generated heat and removed carbon at the same time. By varying the airflow, the carbon content could be controlled. Iron and steel created the Industrial Revolution. They formed the tracks of the Transcontinental Railroad and the trains that roared along them. And they made possible the skyscrapers that came to symbolize the sublime reach of 20th century civilization.
If you imagine a structure to take a wind load, the wind is going to tilt it. And as soon as you tilt it, you bow the outside edge here, and now you're pulling on this curved side, and you're pushing on this curved side. And so that material has to be not only strong on the compressive side, it has to be strong on this side too, and stone won't do. Steel will. A steel building can rock in the wind quite a long way and still survive.
Steel cables act much like rope, at once flexible and strong. The Brooklyn Bridge was the first large-scale structure supported by steel cables, and its sweeping span contains an astonishing 14,000 miles of steel wire. But workers who toiled with other heavy metals, like lead, would soon learn that progress has its price. More steel in the United States is used to make bottle caps than to manufacture automobile bodies. We now return to heavy metals on Modern Marvels. With an atomic number of 82, lead is extremely dense, the best natural shield known to man. Cathode ray tubes from television and computer screens contain enough lead to block harmful radiation. Medical X-rays use lead for the same reason. And a thick enough lead container can even safely store nuclear waste.
As a particle tries to pass through it, it has to collide with a lot of atoms, each of which has a lot of protons, these charged particles, that slow or stop the process. And so it's an extremely good shielding material.
Today, the most common application of lead is in car batteries.
About 80% of the lead that's produced in this country goes into lead-acid batteries. It's still the cheapest form of electrical power for the automobile. And we have over 200 million automobiles in this country. Every one of them has at least one battery.
One of the world's largest deposits of lead ore lies beneath the St. Francis Mountains in southeast Missouri. Millions of years ago, this region was an ocean, and deposits formed in a narrow vein along an ancient tropical reef, a vein 42 miles long and just 500 feet wide. Eventually, shifts in the Earth's tectonic plates covered the sea and the lead vein, with a mountain range that exists today. The metal lies 1,000 feet beneath the surface, and every man and machine used to mine it must descend through this elevator shaft. Large haul trucks, which can measure 40 feet long and 15 feet wide, are dismantled for transport and reassembled underground. These machines will never again see sunlight.
We have to maintain all of our equipment underground. It's not like we can drive it to the nearest service station. We need to change our large tires underground. We even rebuild engines. But all the maintenance needs have to take place underground because we only have shaft access to the mines.
Lead ore's exceptional density supports tunnels 30 feet wide and up to 120 feet high. Hydraulic jumbo diggers with 2 front-loaded drills carry out the first stage in lead mining.
Where we'll go in and we'll drill the rock face, put a series of holes. We'll actually use 75 holes in a rock face that are 2 inches in diameter and drilled to a depth of 12 feet. They're done on a specific engineered pattern to allow for the maximum breakage of that ore material.
Most of the holes are drilled in the center of the rock face. That area will be detonated first, creating a void for other rock to break towards. This single ore face is filled with 800 pounds of explosives. The mine uses 19 different types of detonating caps, each with a different timing delay. The farther it is from the center, the later an explosion takes place, maximizing the cascade effect. Once the rock is blasted free, giant mechanical scalers remove loose material from the walls and ceiling. Each day, 5,000 tons of rock are hauled to the surface. But less than 5% is lead, and a series of steps is required to liberate the metal. First, ore passes through a grinding circuit that crushes it into ever smaller pieces. Different minerals are then separated out in a process known as flotation. Just as laundry detergent latches onto particles of dirt and lifts them away from clothes, a flotation cell forms a chemical bond with its target metal.
The flotation process is both a chemical and a physical process. The collector latches onto the surface of the mineral particle, and as the air bubble comes along, it becomes more of a physical process at that time. A chemical bond attaches a collector to the mineral particle, and a physical reaction between the air and the mineral particle actually brings it to the surface.
Most of the lead we use today was mined years ago and has since been recycled.
Over 98% of all lead is recycled in this country today. So what we're doing is we're recycling that lead that has been produced in the past right back around for reuse.
The majority of recycled lead comes from car batteries. Massive landfills once overflowed with the toxic remains of millions of them. Today, batteries find new life at bunkers capable of holding more than 15,000 tons of shredded batteries. Recycled or mined, lead can be as harmful as it is helpful, a sobering truth dating back to antiquity. Ancient Romans used it in dishes, coins, and vast systems of water distribution. They even flavored food and drinks with the metal, savoring its sweet overtones.
Well, the ancient Romans were in some ways quite addicted to lead. There is a theory about lead playing this part in the fall of the Roman Empire. There are accounts of Julius Caesar not being able to father a child except for one, and his offspring was indifferent to sex and couldn't father a child. So lead could have been a huge component in that.
In the modern era, lead's devastating impact is all too familiar. Beginning in the 1920s, refiners began adding it to gasoline to reduce engine knocking. Workers who made the additive learned firsthand how lead attacks and debilitates the central nervous system.
It was termed as loony metal because in the latter stages of the involvement of the metal in their systems, they started to kind of lose their minds and then eventually died.
Leaded gasoline would endure into the 1980s. In 1995, the Environmental Protection Agency concluded that 5,000 Americans died annually from different kinds of lead poisoning. Today, lead has been banned from gas, paint, and most household items. Lead workers undergo blood tests every 6 months. We're finally learning that lead's value must always be measured by how safely we mine and use it. While lead's history is measured in millennia, the heavy metal zinc is a recent and increasingly important part of our grandest structures. In the 1450s, Johannes Gutenberg used lead to create the first metal movable type, giving the masses access to books. He is reported to have stated, "Give me 26 soldiers of lead, and I will conquer the world." We now return to heavy metals on Modern Marvels. Zinc is placed at 30 on the periodic table, and perhaps no heavy metal has more applications. It fights infections and helps heal surface wounds on the body. Its heat and ultraviolet reflecting properties make it an essential ingredient in sunblock and on the space shuttle's heat-resistant tiles. And it fuels commerce by making die castings for the automotive, electrical, and hardware industries. But zinc's primary role is in corrosion resistance. It extends the life of our modern steel-based infrastructure. When coated with zinc, cars, ships, buildings and bridges, any steel structure will survive for years or decades longer.
Zinc is used to galvanize steel, which puts a layer of zinc on top of the steel, and then when the oxygen or water in the air begins to attack the zinc, it quickly forms an oxide skin that prevents further attack. So it's a wonderful material to inhibit corrosion.
Once mined and milled, zinc ore proceeds to the smelting furnace. There, carbon monoxide reacts chemically with the ore to form a zinc vapor. That gas is then condensed. Finally, it's reheated into molten zinc and ready to be cast into everything from 55-pound slabs to 2,400-pound ingots.
The operator now is using skimming boards to remove dross from the surface of the ingots. The dross forms because the zinc has been exposed to air and forms a frothy material that ruins the zinc surface. We want the product to go out with a nice smooth surface, so he skims those off with skimming boards and then closes the top of the ingot mold and allows it to slowly cool and solidify.
Larger ingots are shipped to galvanizing companies to be alloyed with steel. But before steel is galvanized, it must be thoroughly cleaned.
We have a sulfuric acid bath here. It's about 160 degrees, about 10 to 12% sulfuric acid. We use this to remove any rust that might be on the steel. We're trying to get the steel as clean as possible before the galvanizing process.
Here at Young Galvanizing near Pittsburgh, the galvanizing kettle is 48 feet long, 5 feet wide, and 8 feet deep, big enough to submerge the largest pieces of steel. The steel is immersed in zinc until it reaches a bath temperature of 840 degrees Fahrenheit. The zinc and steel actually form a metallurgical bond, an alloy that will resist rust and corrosion for many years to come. Zinc has thus fulfilled its role as the great protector. Just as zinc galvanizing supports our visible infrastructure, copper forms the hidden foundation of modern life. Our world is inconceivable without electricity, and every inch of every electrical system depends on the unique conductive properties of copper wiring.
Copper in today's world is intricately woven into the fabric of our society. The fact that roughly 400 pounds of it exists in the everyday home and that people use it unknowingly in electronics and telephone communication is permeated our culture in a way that has never been seen before in history.
For the past century, the world's largest source of raw copper has been a gargantuan open-pit mine in Utah.
You're looking at the largest man-made excavation on Earth, the Bingham Canyon Mine. From the point that I stand here, it's almost 2.5 miles to the other side. And in depth, it's over 3/4 of a mile deep. You could stack 3 Empire State Buildings on top of each other, and they wouldn't reach the top.
The Bingham Canyon Mine is one of the very few man-made structures visible from space. Bingham has yielded more than $6 billion in copper, more than the California and Klondike gold rushes and Nevada's Comstock lode combined. Each day, 450,000 tons of material are removed from the pit. But Bingham has been so heavily mined that today its ore contains just 0.6% copper. After the rock is blasted free and crushed, a series of conveyor belts carries it 5 miles to the concentrator. There, flotation cells separate out a liquid that's 28% copper. The liquid is pumped 17 miles to a smelter, where furnaces refine it to 99.6% purity. and it's cast into 700-pound plates called anodes. But 99.6% is not pure enough. Racks of anodes are lowered into an acid solution interlaced with stainless steel cathodes. For 10 days, an electric current passes between anode and cathode, causing copper ions to dissolve off the anode and redeposit on the cathode as 99.99% pure. 1 ton of ore from the mine has yielded 12 pounds of refined copper. Copper is easily shaped, molded, and drawn into electrical wires. Residential wiring is covered in white, orange, or yellow insulation to identify its gauge. Commercial bundles contain up to 61 separate strands to deliver high voltage power.
If we had one solid conductor, something of this diameter, it would be so difficult to bend, to pull around corners to get to where you need to go. It would be difficult to work with. When you have a stranded conductor of many individuals, it becomes flexible enough that you can pull it through conduits to get to where you need to go.
If we live in a global village, copper is the glue that connects us. It allows communication around our world. The heavy metal nickel is helping us travel to other worlds. Copper is the only metal besides gold that has a distinctive natural color. Other metals are either gray or white. We now return to heavy metals on Modern Marvels. The heavy metal nickel has an atomic number of 28, and its unique combination of lightweight, corrosion resistance, and extreme strength have made it highly valued. Much of the Earth's nickel deposits date back to an ancient cataclysmic event that shook a region in what is now eastern Canada.
A meteor struck the ground near Sudbury, Ontario, somewhere around 2 billion years ago. And in the process of striking the ground, brought the nickel that it had in it, but also caused the nickel from under the ground to come up through flows from the Earth's interior.
30% of the world's nickel comes from the giant impact crater in Sudbury. And much of that nickel is devoted to high-performance aviation. Nickel is the indispensable element in jet turbine blades, devices that must rotate at 10,000 revolutions per minute for up to 16 hours without deforming in the slightest, and whose failure could cause death and destruction.
Here you have a blade spinning around at enormous speed, and if you've ever spun on a merry-go-round, you know how hard it is to hold on. The outside of a turbine blade has to hold on to the inside of a turbine blade at 1,000 degrees, and it has to do this in the presence of a streaming flow of hot reactive gases.
Nickel superalloys used in turbine blades like these are actually stronger at 1,200 degrees than at room temperature. The process of making turbines, known as investment casting, involves a mix of ancient and futuristic technologies.
The investment casting process is very old. It was essentially developed by the Egyptians. They used it to make a lot of their statues. They'd take beeswax, form the statues out of the beeswax, and then probably went down to the Nile River, got some clay, and shaped the clay around it. Then they'd melt gold or silver or bronze and pour it into these clay molds.
Today's engine castings are made using the same process, but with much greater precision. Molds for turbine blades are computer designed, with prototypes created by a laser that cures photosensitive resin in layers 4/1000ths of an inch, 1/3 the width of a human hair. The efficiency of a jet engine is directly related to its operating temperature. The more heat turbine blades can withstand, the farther and faster a plane can fly. Military jet engines can operate at well above 2,000 degrees Fahrenheit, and there are constant efforts to raise the ceiling even higher. Heavy metals have always helped us advance our goals and extend our reach.
They've been on the cutting edge all throughout the 20th century and certainly will be through the 21st century as well. And whether that's in high-tech metals for aircraft applications or spacecraft, they are involved in almost everything that we do and everything that surrounds us.
Our long kinship with heavy metals made possible the giant leap of July 20th, 1969. When Apollo 11 landed on the moon, the lunar module was coated with a nickel-steel heat-resistant alloy to protect it from the sun's rays. The heavy metals that originated in deep space have been transformed by mankind very bodies. They sustain modern life and are essential to every advanced tool built by human beings. They can take us to the heavens or destroy us. Now, heavy metals on Modern Marvels. They come from the dawn of the cosmos and the fiery hearts of dying stars.
Heavy metals are cooked in the center of a star. As a star is born and lives its life, it comes to a phase at the end where a bunch of processes happen very rapidly and the star explodes, and in exploding scatters out a group of heavy metals that reach all the corners of the universe.
National Defense Stockpile. A $10 billion collection of materials ready in case of all-out war. In a national emergency, no metal would likely prove more decisive than uranium. With an atomic number of 92, uranium is the heaviest of all elements, 18.7 times denser than water. Its naturally occurring radiation generates tremendous power from within the Earth's core, more than twice the level of global human energy consumption.
You can account for about 30 trillion watts in the form of radiation coming from the uranium-238 that was captured when the early Earth was formed in the core. That now acts like a small nuclear reactor. It's a natural source of heat that has to make its way to the outside of the planet, and it brings up quite a bit. And volcanoes today are living proof that something in the core of the Earth is generating a lot of heat.
The introduction of the atomic bomb in 1945 heralded uranium's immense potential as a destructive force. But splitting the atom also unleashed a vast, peaceful source of energy. There are 103 nuclear reactors operating across the United States, generating nearly 20% of the nation's electricity. worldwide. 430 reactors help power 31 different countries. Like other metals, uranium is extracted through either underground or open-pit mining. The ore is pulverized, then treated with acid to dissolve. Metals now found on Earth came from one of two sources. Space debris that collected as the planet formed 4.6 billion years ago. Or meteorites that have since struck. They endure through an eternal life cycle of endless transformation.
They're found, manipulated, relied upon in ways that we totally take for granted, and then they're discarded and reused again. They're completely recyclable in most cases.
Metals make up 2/3 of the known elements. An element is defined by the number of protons, neutrons, and electrons that form its atoms. The periodic table lists elements in ascending scale based on atomic number, the number of protons in each nucleus.
Periodic table is a way to organize the elements that occur naturally in the universe and ones that can be created by unnatural processes into a sequence that starts with the lightest element, hydrogen, and progresses up to the heaviest natural element, uranium. And on the progression, somewhere around 26, iron, is a breakpoint where anything heavier could be regarded as a heavy metal.
From the earliest days, human progress has been tied to the mastery of metals.
The advanced civilizations all use metals for cooking their food, for transportation, for work, for agriculture, for defense.
The average American baby born in 2006 will require 45,000 pounds of metals during its lifetime to sustain its standard of living. Heavy metals such as iron, lead, zinc, nickel, and copper are so essential to America's economic and military might that they are stored in the